What's going on, guys? Okay, so in this video I'm going to be walking you through some exam style questions using the diffraction grating formulas. So make sure that you understand diffraction gratings before watching this, and I'll just walk you through a couple of questions so you can see my thinking behind tackling the questions. Okay, so just a quick recap. First of all, D stands for the slit separation in the diffraction gratings, the distance between each slit. Theta n is the angle at which the order that you're looking at you'll see. So if this is the order number 1, it's the angle between the central maxima outwards to the order 1. N is going to be the order number, lambda is going to be the wavelength. And obviously the slit separation D is also equal to 1 over n. Okay, just make sure you're happy with that, and now we can tackle the questions. Alright, so first of all, question 1. A grating is labelled at 500 lines per millimeter. Calculate the spacing of the slits in the grating. Right, so first of all, you know there are 500 lines per millimeter. That's not the same as how many lines there are per meter. So don't forget, over here, this capital N is the number of lines per meter. So if you've got 500 lines per millimeter, if I gave you a meter stick, how many would you have? You'd have way more. So first of all, let's find out how many would there be in a meter. So we should recognize that there's going to be 500 times by 10 to the 3 lines per meter. Yes, because make sure you're happy with that. Yes, because there's 1,000, yes, inside 1,000 millimeters inside a meter. So therefore, every single one of them has 500. So we've got that many lines in total. Now let's calculate the spacing. So first of all, we know the formula is going to be slit separation D is equal to 1 over n. So it's equal to 1 divided by 500 times by 10 to the power of 3. Okay, let's bang that into a calculator over here. So it's going to be 1 divided by 500, 10 to the power of 3 over here. We're getting the answer of 0.0000005 noughts. So that 5 noughts, 1, 2, 5 noughts, 2, which is the same as 1, 2, 3, 4, 5, 6. 2 times by 10 to the minus 6 meters is a slit separation. Okay, easy stuff for the first one. Question 2. Monochromatic light is aimed straight at the grating and is found to give a first order maximum of 15 degrees. Okay, calculate the wavelength of the light source. Right, so if I was you, let's draw it out over here. So let's draw monochromatic light. Don't forget, monochromatic means one color. It's aimed at the diffraction grating. So here it is. It hits the diffraction grating. And the first order, so don't forget this is the central maxima where n is 0. The first order is here, n is 1. The first order here, it's at 15 degrees. So this one over here is 15 degrees. And there we go, so it's 15 degrees over here. Don't forget this is n is 1 at the bottom as well, but I'll just draw it so that we can visualize the problem. Calculate the wavelength of the light source. So let's use this equation because it's the only one which has the wavelength in it. So d sine of the angle theta n is equal to n lambda. Rearranging it then, therefore lambda is equal to d sine of the angle theta n divided by n, the order number. N goes underneath. So that becomes, so don't forget it's the same grating as before, 2 times by 10 to the minus 6, that's the grating, times by sine, and don't forget, for the first n is 1, so obviously theta 1 is going to be 15 in this case, sine of the angle 15 divided by 1. Okay, so over here in a calculator, 2 times 10 to the minus 6, there we go, times by sine of the angle 15. Okay, I'm going to get the answer of, how many is there? Oh, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and then it's a 5, 2. Okay, which is going to be 1, 2, 3, 4, 5, 6, 7. That's going to be equal to 5.2 times by 10 to the minus 7 meters. That's the wavelength. Lambda is equal to this much. Easy stuff. So let's highlight that so make it look nice and jazzy. There we go. So we know what we're doing. Okay, next one, question 3. Calculate the position of the first order maximum when red light of wavelength 730 nanometers is shone directly at the grating. So calculate the position of the first order maximum when red light of wavelength 730 is shone at that grating. Okay, so we're going to draw the diagram again. So the red light hits it. Here's the grating, bang, and there it is. There we go. Still the first order, so this is n is 0, n is 1, n is 1. So if it's asking for the position, it's actually asking for the angle. So it's really trying to get you to work out what theta 1 is here. What is that theta 1 here? What is that angle? So let's rearrange that formula. So d sine of the angle theta n is equal to n lambda. Oh, can't spell sine. Right, so therefore, plug in the values in. Therefore, theta is equal to, well, theta 1 is the first order, the angle at which the first order is seen, is equal to sine inverse, open bracket, n lambda divided by d, in this case over here. So yes, so it's going to be sine inverse, it's going to be open bracket 1 times by what's the wavelength? Careful, the wavelength is now 730. So 730 nano, get rid of the nano, times by 10 to the minus 9, divided by the slit separation. Yes, what is the slit separation? Same as before, 2 times by 10 to the minus 6 in this case. Okay, into a calculator, 730 times 10 to the minus 9, divided by 2 times 10 to the minus 6. Good. Sine inverse the answer. It's equal to 21.4. So 21.4 degrees. That's the angle which you'd see that first order if you shine the red light of wavelength 730 nanometers onto it. Super. Okay, next question. And it gets a bit harder now, yes? So really try and visualize the question before we tackle it. Right, okay. Give you a bit of time to read it. The longest visible wavelength is that of red light, lambda is equal to 750 nanometers. The shortest visible wavelength is violet, where lambda is equal to 400 nanometers. Use this information to calculate the width of the angle into which the first order spectrum is spread out when white light hits the grating. Okay, so this is quite a lot to take in. Basically, though, it's telling you that you're going to shine white light into it. Don't forget, white light consists of all the colors. Yes, Richard of York gave battle in vain. So from red all the way to violet. It hits the grating, and obviously the red light will be diffracted by a certain amount, and so will the blue light. So the red light will actually go further. Yes, will go quite a long way. The angle is going to be diffracted by a large amount. And also you can see the reason why, because look, if we have d sine of the angle theta n is equal to n lambda. Look, as the wavelength is increased, don't forget red light has the longest wavelength, sine theta also increases, provided the other variables remain constant. So red light will have the greatest angle, yeah, and then the violet light inside white light, because that's going to be inside it, will have the least. Okay, there we go. But this is both for the first order. So obviously there's still the central maxima over here where n is equal to 0. This is going to be n is equal to 1 for the violet, and this is also going to be n is equal to 1 for the red. So don't forget that's the reason why we have 2 for the same order, because red light diffracts by a certain amount, and obviously the violet light diffracts by a certain amount. The question's asking you, what is the spread of this? The spread of the first order spectrum. So it's trying to get you to answer and get you to work out what this value would be here. So if I was to, let me just erase that for a minute. So we're trying to work out what this will be. We're trying to work out what this will actually be over here, this value. What would it be? How will we do it? Right, the way we can do it is the following. Well, if I find the angle for the red one and I subtract the angle for the violet one, it would tell me the answer, because that will tell you the spread of it. And it's quite difficult to obviously work it out from this question, but obviously, you know, you have to practice on deciphering the question. That is a skill in the A-level here. Okay, right, so let's try and do it. Let's do that. Let's find the angle which the red one is observed. So we know that d sine of the angle theta 1 for the red light is equal to n lambda. Okay, so theta 1 is equal to sine inverse, open bracket, n lambda divided by d. Okay, and I'll just turn it because it's for the red light. So theta 1 for the red light, subscript, so you know it's for the red one, is equal to sine inverse. What's the order number? It's still 1. It's still n is 1 for both of them, yes? And n is 1 for both of them. So it's 1 times by the wavelength of the red light, 750 times by 10 to the minus 9. Don't forget, red light is here. Divided by the slit separation. The slit separation is, it's the same one as before. It's still going to be 2 times by 10 to the minus 6. 2 times by 10 to the minus 6. Okay, let's do this in a calculator. So it's going to be 750 times 10 to the minus 9 divided by 2 times 10 to the minus 6. Good. Sine inverse the answer, 22. So this angle for red light, theta 1 for the red light, is equal to 22.02 degrees. Okay, let's do the same thing again let's find this one. So let's find for the violet light now. So originally we found this one, yes. Now we finding the violet one. So for the violet light, let's find that angle. So it's going to be d sine of the angle theta 1 is equal to n lambda. Right, so theta 1, same formula rearranged, sine inverse, but obviously n lambda divided by d. Obviously, sorry, lambda is now going to be the violet one, 400 nanometers. So theta 1 for violet is equal to sine inverse, open bracket, 1 times by 400 times 10 to the minus 9. So it's a bit small. Everyone, make sure 400 times 10 to the minus 9 over there. And you should be familiar with the wavelengths of red to violet. Yeah, it's just familiar with them in case that it comes up in the question. Divided by the separation. Oops, no, that's not. Let's go. I didn't do divided by, just inside the bracket, 2 times 10 to the minus 6. We're doing to the sine inverse of all of that. So it's going to be 400 times 10 to the minus 9 divided by 2 times 10 to the minus 6. Okay, sine inverse the answer. There we go. That's a 6 there, yeah. So we're getting theta 1 is going to be equal to 11.53. Okay, so we know this one is 22.02 and this one is going to be 11.53. So therefore the width, the difference, yes, between that for the red and the violet is going to be the answer. So it's going to be obviously 22.02 minus 11.53. So 22.02 subtracting the answer is equal to 10.48 degrees. That's my answer over here, or 10.5. So there we go. Is that right? Yes. Yeah. There we go. Yeah. Make sure we're happy with that. Yes. We've got that answer. Yeah. Just make sure you're happy with that. Okay. Right. Fine. So that one was quite tricky. So make sure you spend the time reading the question yourself and draw the diagram. I can't stress how many times I see kids just think they're going to get the formula and throw it in. Draw the diagram to visualize the problem. It is quite abstract. Okay. Right. Scrolling down for the next one. Okay. Right. So. Okay, so I'm just gonna, yeah, fine. We can read that. We don't need to rub anything off. A grating is illuminated with a parallel beam of light of wavelength 550 nanometers. The first order maximum is in the direction making an angle of 20 degrees with the straight through direction. Calculate the spacing of the grating slits. Okay, so we're trying to find what D is. D is. Okay, so let's draw it again. So the light hits the diffraction grating, it spreads out. The angle is 20 degrees. This angle for the, which order is it? First order, it's still n is equal to 1, n is equal to 0 over here. Fine. So now we're over here. Let's do this. So this one's going to be, we're going to work out the spacing. So d sine of the angle theta n is equal to n lambda. D is equal to n lambda divided by sine of the angle theta n. Okay, first order, so it's 1. Yes, times by the wavelength, we've got 550 nanometers, 550 times by 10 to the minus 9, divided by sine of the 20. Voila. So over here, it's going to become 550, so 10 to the minus 9. Good, divided by sine 20. There we go. I'm getting the answer of the slit separation going to be 0.1234516, which is 1, 2, 3, 4, 5, 6, which is the same as 1.6 times by 10 to the minus 6 meters. Yes, let me just double check I've got that right for question 5. Yes, perfect. Okay, that one's pretty easy compared to the one before. The other one was very abstract. All right, question 6. There we go, question 6. It's on 2 pages, but hopefully you can still read it. What would be the angle of the first order maximum if a grating of slit spacing of 2.5 times by 10 to the minus 6 meters were used with the same light source? So what would the angle of the first order maximum be if a grating of slit spacing 2.5 times by 10 to the minus 6 meters were used with the same light source? Okay, so they're now shining the same light source going in, hitting the diffraction gratings. Okay, so it hits the diffraction gratings, and you're trying to now work out the angle. You're trying to work out this angle. For the first order, don't forget, it's n is 1, this is n is 0. Okay, so what would the angle be? So d sine of the angle theta n is equal to n lambda. Right, so therefore theta n is equal to sine inverse, open bracket, n lambda divided by d. N lambda divided by d. Right, okay, so now from here, let's go for, what have we got? We've got, so sine inverse n is 1 times by lambda. What then earth is lambda? Oh, it's going to be same light source, so obviously its name remains 550 times nanometers, 550 times by 10 to the minus 9. Good. Divided by the slit separation for this one. The slit separation, we've got it is here. 2.5 times by 10 to the minus 6. Very good. Over here, so it's going to be 550 times 10 to the minus 9 divided by 2.5 times 10 to the minus 6. Good. Sine inverse the answer. I'm going to get 12.7. So theta, obviously this is theta 1, obviously. Yes, theta 1 for this one is going to be 12.7 over here. 12.7. Let me just check my answer if it's correct. Yes, it's 12.7 degrees. Very good. Excellent stuff. Okay, the next one. Let's scroll down. It's going to be 7. Calculate the wavelength of light that would give a second order maximum of theta is equal to 32 degrees. Okay, so calculate the wavelength of light that would give a second order maximum of 2.5, or second order maximum of theta is equal to 32 degrees with a grating of slit spacing 2.5 times by 10 to the minus 6 meters. Okay, so let's go. We're trying to work out wavelength now. So we know that it's the second order now. Notice it's changed. So the light comes in, hits a diffraction grating, and obviously it's over here. This is n is 0, and n is 1, and now we're at the second order, n is 2. This one over here, n is 1. This one is going to be equal to n is 2. So we're going bang, bang over here. So we're trying to work out the wavelength of light if this is 32 degrees to the second order. What is the wavelength of light? Right, okay, so it's the same formula. D sine of the angle theta n is equal to n lambda. Notice now, n is not 1, n is 2 now, because it's the second order in this case. So now we're going to rearrange the formula then. So it's going to be wavelength lambda is equal to d sine of the angle theta n divided by n. Yes, right. D was going to be 2.5 times by 10 to the minus 6 times by sine of the angle, what's theta n? Well, yes, so it's sine of the angle 32, because that is the angle at which the second order appears, 32 degrees, divided by n. What's going to be the order number? 2. Bang it into a calculator. Let's go. 2.5 times by 10 to the minus 6 times by sine of the angle 32 divided by 2. The answer I'm getting is going to be equal to 0.1. How many? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 zeros, 6, 6. Yes, which is the same as 1, 2, 3, 4, 5, 6, 7, which is the same as 6.6 times by 10 to the minus 7 meters. Very good. Yes, I think that's right. Let me double check the answer, people, if I'm right. Oh, yes, 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 yes. Perfect. Excellent stuff. Okay, right, so we're done. So obviously, make sure you have done the thinking yourself. Please don't think that you're just going to see the same question in an exam. Understand how each question works. Make sure you draw out the diagrams and obviously show you're working out over here. It's all about the wording. Some of these questions are very wordy and therefore, like, it's really hard to decipher what they're asking you. So that's why take the time, underline the key words. Like, if you're reading the question, you know it's that you can maybe underline, you know it's the wavelength, second order, 32 degrees, and this bit over here. Highlight the information that you might use in the calculation. Yeah, and that's it. And obviously, everyone, make sure you hit the like and subscribe to keep my channel going. Comment below if you get stuck or if you think I've done something wrong, but it should be, I think all my answers are right in this case over here. And yeah, just let me know if I can help you any more. If you know anyone who's still struggling in physics, don't forget to share my channel with them. Good luck, ciao, ciao, and goodbye. Bye-bye. Oh, let's stop streaming. Oh, okay.